Welcome back to our series on multivariable calculus. In this episode, we're going to be looking at the integrals of space curves, namely the integrals of these vector functions that we've been looking at. Now, of course, we already learned that the derivative of a vector function is fairly straightforward. You simply take the derivative of its three component functions. In the same way, integration will simply be the integral of the three spatial functions that define the vector. Integration has fewer applications than differentiation, but of course its greatest application is its ability to do the antiderivative. And that's really what we'll be applying it to. Suppose I knew what r prime of t was. And of course, r prime of t, as we've already learned, is going to be f prime of t, g prime of t, and h prime of t. What we're most interested in is reforming the original rt that this came from. And of course, that's not very difficult. The integral of r prime t dt should give me that. And that means I need to do the integral of f prime of t dt, the integral of g prime t dt, and the integral of h prime t dt. Of course, we know what we'll be missing if we simply evaluate these integrals based on the functions that are sitting here. And that is, we'll be missing the initial condition, that is, where rt really began at t equals 0. And so one thing you'll have to remember to do is include your constants of integration. In essence, the answer to this is going to be that rt is equal to, this will be f of t plus f of 0, g of t plus g of 0, and h of t plus h of 0. These constant will be filled in by a boundary condition you'd be provided with, and that is, if you were provided with this as a question, hey, find the original vector function from its derivative, you would also be provided with an r at 0 is equal to a specific f naught, g naught, h naught trio. And that means you could substitute those in for these final functions so that your integral would actually contain the initial conditions that would actually replicate rt, a specific rt, as opposed to a general rt. And what I mean by a general rt is if you ignore these integration constants, all you'll end up with is all of the potential rt's that have this as their derivative. That is, this will give you the vector that runs tangential to every point on the curve. But it won't begin at the right location. That is, it won't begin where rt actually begins. So the one caveat in moving from two-dimensional integration to three-dimensional, particularly this vector integration, is the idea that even though we have one variable t, its initial conditions come in three pieces, which is it independently informs us of initial conditions for f, g, and h. So you have to take that into account when you perform these integrals.